Good morning, everyone. Good to see you back. We're going to get started in a second. People are trickling in still. But I'll give you an intro in the meantime. So today, big day, we're going over differentiation, and we have a lot to cover. We're going to try and do all of differentiation in just under 3 hours. So we have to cover very quickly limits, the definition of the derivative, rules of differentiation. Then we cover applications of derivatives, optimization, increasing and decreasing regions, tangents and normals, all of those things. And we'll do the HL content, which are a few more derivative rules, plus more applications of derivatives like related rates, L'Hopital's rule, and implicit derivatives, and also proofs with derivatives. We're going to do some of those as well. So today, because there's so much to do, we are not going to take as much time on every exercise, on every problem. What I'm going to do is give you for each of the exercises and problems that we come across, I'm going to give you a head start, about the third of the time you would need to solve it to get ahead of where I am. And then I'm going to start straight away so that I can get everything done in the time that we have. So I would recommend you do is, start the problems and exercises, try and get as far as you can on your own. And then I'm going to start, maybe a minute after you. And you can not listen to me, you can turn your volume down and just keep going. But I do have to keep the pace up. But that shouldn't deter you from trying to solve the problems. Okay, so with that said, we are going to get started. And we're going to start by talking about the basic concept of a limit, because we need limits to formalize our understanding of what happens with derivatives. And limits look like a fancy thing, and it's basically nothing more than a fancy notation of asking the question, what happens to the function as I get close to a particular point? Because there are going to be some functions that, and we've seen these before, are undefined at specific points. We know, for example, that if I have 1 over x, it's undefined at x is equal to 0. But we have, even in that context, ask the question, well, what happens to 1 over x as x gets close to 0? And we realize that we have an asymptote, and the function is going to go to plus or minus infinity. And limits, we can do that in general, but basically it's going to allow us to observe what happens to the value of a function as we get close to a point. So for example, if I had the limit as x approaches 3 of x squared plus 2, I mean, this is boring, there's nothing special happening in this limit, but I simply plug in x is equal to 3, and I get 3 squared plus 2 is equal to 11. Now, slightly trickier example, and this is supposed to be a 3 here, is the limit as x approaches 3 of x times x minus 3 over x minus 3. Because this function is undefined at x is equal to 3, because the denominator would be 0. But when x is not equal to 3, when x is approaching 3, then this just simplifies to x. And so the limit tends to 3 as x approaches 3. Now, another type of limit, or limits at infinity, if I let x go to infinity and I ask myself, well, what happens to the function 3x plus 2 over 2x minus 1? We've seen this before. This is a rational function with horizontal asymptotes. It's going to behave as if it was just 3x over 2x. The constants at infinity are going to make no difference. And that simplifies to just 3 over 2. Okay, so you're supposed to know, although it doesn't really show up on exams, how you would find the limit from a graph. So let's say here I have I have a function that has a gap in it at 1, comma 2. There's a hole in the function. It's undefined there. All right, so f of 1 is undefined, but the limit as x approaches 1 of f of x is defined. It's just basically saying, as I get closer and closer and closer, what do I find, as I approach this point? And it tends towards 2, okay? So it's kind of like the limit is basically asking, what value does it seem like I'm going to get to if I keep going in the direction that I'm heading without getting to the destination? Okay, so on this graph, the limit as x approaches 1 is 2. The limit as x approaches infinity is 3 over 2, as we see this function is approaching the horizontal asymptote. And the same thing for the limit as x approaches negative infinity. It's also leveling off and approaching that asymptote. I'll give you 10 seconds to think about this, and I'm going to immediately go over how to do it. So I have a graph here that shows me y is equal to f of x. And I see that this graph has a hole at 1, comma 3. And the question is asking me to find the limit as x approaches 1 of f of x. So what does the function do as I get closer and closer to x equals to 1? It gets closer and closer to 3. So the limit is 3. Now, as x goes to infinity, I'm noticing that this line is leveling off and flattening out. It's actually going to form a horizontal asymptote at y is equal to 0, so the limit is going to be 0. Now, you also should know how to find limits from a table, okay? And these are really, really easy. The table is just going to tell you different values of x getting closer and closer to some particular value, and what the values of the function are at each of those points. So if I have x equals 2.9, 2.99, 2.999, and I see that f of x is doing 8.41, 8.9641, and then 8.9964001, I can tell that this is getting closer and closer to 9. I can just eyeball that, okay? And it's getting closer and closer to 1. And specifically, you don't need to know this like intricacy of limits. But the limit, the limit goes to 9, means that I can get closer and closer to 9 just by picking a closer and closer x. And there's no upper bound on or no lower bound on how close I can get to 9. I can get as close as I desire. That brings us to slope. We're ready to start with calculus. So we already know from straight lines that the slope can be calculated. Slope of a straight line can be calculated using the equation rise over run, or y2 minus y1 over x2 minus x1. And differentiation is all about finding the slopes of functions that are not straight lines. And the way we're going to do that is we're going to say that obviously the slope of a function is going to be changing. You can see the slope here is not the same as the slope here. The slope of the function is going to be changing in general. So what we're going to do is we're going to say, okay, we're going to need to find the slope at a specific point. And we're going to have to say, okay, the slope here at this x value, okay? And the way we find that slope is by drawing a tangent to the graph, which is a line that touches the graph there with the same slope. Okay, so it kisses the curve there, and it's like if you zoomed in at that infinitesimally small point, the two lines would be parallel. Okay, they'd be parallel and also overlapping, and then that's a straight line whose slope we can find out, right? Now, what I want you to realize is that it's very difficult to draw a perfect tangent, by hand. I can't take my ruler and really set it perfectly. That's a difficult process. What I can do, though, mathematically, is I can draw a line that goes through the point that I'm interested in and some other point somewhere else on the curve. And that's what you're seeing here in this dotted line. And then what you can do is, well, you'll notice that this straight line, this dotted line, has a slope that's not so far off from the slope that I've drawn in the solid line. And specifically, that slope gets closer and closer to the true slope when the distance from the point gets smaller, okay? So what's actually happening here is we're making an approximation for the slope by drawing a segment. We're drawing a line that goes through the point and somewhere else on the curve and measuring its slope. And that approximation for the slope is going to get better as we bring the points closer together. Now, calculus, basically, differentiation, is all about letting that difference in distance, let's put that in a limit and let it go to 0. What is going to happen to this approximation of the slope as the distance over which I'm looking at it goes to 0? Another way of thinking about it is as I zoom in more and more to this graph, what is my approximation of the slope going to tend towards? What am I going to converge to in my approximation? And that is going to be the value of the derivative at that point. Now, formally, this is a definition that SL students need to be familiar with. Only HL students need to use it, and we're going to talk about that at the end of the session. But what I do is I imagine on a curve having I imagine I have a curve of f of x, and I draw a triangle, okay? And I have a triangle that is at some specific point x, and I let the base of the triangle be h. All right, now this coordinate here is x, comma f of x. And because this is a right angle triangle with h over here, this is going to be x plus h, and then f of x plus h, okay? Which means the slope of this triangle, if I use rise over run, I take the difference of the y coordinates, f of x plus h minus f of x, and I'm going to divide that by the base of the triangle, which is h, okay? So that's h. And that gives me an approximation for the triangle. And then what I realize is that the smaller I make this triangle, the smaller the base gets, the better the approximation is going to become. And I can show you a triangle, with just a slightly better approximation that looks something like this. And we can already see that slope is much closer to the actual slope at that point than the original line that I drew. It looks almost like a perfect tangent now. So mathematically, if I set the limit as h goes to 0 of this approximation of the limit, if I put that under a limit with h goes to 0, it's going to approach the true value for the slope. It's going to give me the true value. And you can actually do that algebraically. You can plug it in and use some basic algebra rules. SL students, you don't need to know how to do this. If it's helpful to you to look at this, you can take a look. But really, every derivative rule that we have has come from this definition. We're going to take a specific function, we're going to plug it into this definition, which essentially is doing nothing more than taking right-angled triangles and trying to make them smaller and smaller and seeing what happens to the rise over run. And we're going to build all these derivative rules, and then we can start putting them together in different ways and combining them using rules that we've also derived using this formula. So this kind of is the foundation of everything that we know from differentiation. Okay, so now that that is introduced, a word that you should be familiar with is this word gradient or slope, okay? And we talk about the gradient of a function to be the slope at a particular point. And because the slope of a function changes, what we can do is we can say that the slope, let's say the slope m, depends on x. M is a function of x. And we typically denote that function f prime. F with this prime to denote the derivative of f. And that way, if I have a function that's not f, I can just write, if it's g, I can write g prime, etc. Okay? So it's nothing more than a function that tells me what the slope is at a particular point. And the way that function was determined was using the rule that we just talked about, using that limit definition. Now, for example, I might have a function whose derivative is f prime is equal to 3x squared minus 1. Okay? So the slope when x is equal to 1, again, I don't know why that's a 2, f prime of 1 is equal to 3 times 1 squared minus 1, that's equal to 2. Okay, so the slope, as you can see on this diagram, is equal to 2 for that function. And if you want to play around with this, you can go back to the slides and you can move this around and see how the gradient changes at different points. And notice that the gradient, we're going to talk about this a bit later, is getting towards 0 here. Gradient is kind of flattening off, and the same thing here. Okay. So I'm going to give you 10 seconds to do this. Okay, so I have the derivative of a function is f prime of x. F prime gives me the slope of a graph at particular values of x. So all I have to do is plug in x is equal to 3. And I'm going to get 3 squared minus 3, which is 9 minus 3, which is 6. That's my answer. 6. Okay, another interpretation of the derivative, or another mental model that you have to have in mind, is that the derivative also represents the rate of change of a function. And when I say rate of change, I just mean how fast the thing is changing at that particular moment. So I want you to imagine you're in a car and the car is accelerating down the highway. So your speed is changing, you're going faster and faster. At every moment, though, if I were to freeze time, there is a speed at which you're traveling at that moment. I can look at your speedometer in the car, and you have a particular speed, and that speed is the rate of change in your position. Actually, the speed is the rate of change in the position, and we'll talk about that when we do kinematics. But the point is, even though something the rate itself can be changing, the rate of change might not be constant. Using calculus, we can find the rate of change at a particular instant. So if I had, for example, a sphere whose volume was given by 4 over 3 pi r cubed, okay, that's any sphere, then if I took the derivative of the volume with respect to r, I would write dv by dr, that's the notation for the derivative. That gives me the rate of change in the volume with respect to the radius. So again, 10 seconds to do this. Okay, so I'm looking for the rate of change in the pool's volume when t is equal to 8 minutes. And I have dv by dt, which is the rate of change of the volume with respect to time. So all I have to do is take my time, which is 8 minutes, and plug it into negative 3 to the negative t over 4, so negative 8 over 4. That's negative 3 to the power of negative 2, which is equal to negative 1 over 3 squared, which is negative 1 over 9 is my answer. Okay, with that said, we're ready to go over all of the differentiation rules that we know. And I'm going to move through these pretty quickly because I don't have time to prove them to you, and there's nothing really particularly interesting to talk about. So I'm going to take like literally 30 seconds to a minute for each of these until we get to, let's say, the chain rule. That's maybe a bit more interesting. So the derivative of x to the power of n when n is an integer. Okay, so if I have x to the power of 6, then its derivative I can find by taking the power down from the function, putting it in front, and then subtracting 1 from the power that I had. So the formula tells me that the derivative of x to the n is n x to the n minus 1. It's in your formula booklet. So for example, if I have x to the 5, the derivative is going to be 5x to the 4. 5 comes down, and I subtract 1 from 5 to get 4. Now for something like 1 over x cubed, I recognize that is x to the minus 3. So what do? I bring down the minus 3. I have negative 3x to the power of negative 3 minus 1 is now negative 4. So negative 3x to the negative 4. Also, some rules about derivatives of sums and scalar multiples. When I say scalar multiples, I mean I'm not multiplying by a function, but by a constant number. So if I have the derivative of some constant number times a function, I can just take the number out, the a comes outside, and I'm going to get a times the derivative of f. It doesn't really change anything, it just stretches the entire function. Same thing for the sum of two functions. The derivative of a sum is the sum of the derivatives. And the derivative of, I can combine these two rules together and say the derivative of a times f of x plus b times g of x is a f prime of x plus b g prime of x. These formulas are not in your booklet, so you have to just remember really that I can split up sums under the derivative, and I can pull out constants. I can factor them through the derivative and just leave them on the outside. I can't delete them, they're still important, but you don't have to do anything special with them inside the derivative. So for example, if I have f of x is equal to 3x to the 4 plus 2x squared, I can write that as 3x to the 4 plus 2x to the minus 2. And I bring down the 4, I get 4x cubed minus, and then I'm going to bring down minus 2, so minus 4x to the minus 3. Okay? And I don't know why I said 4. It was 12 for the first one because there's already a 3 in front, so 12. Okay, so I differentiate 4x cubed, I bring down to 3, I get 12 x squared, and then I have minus, because I have a negative 2 there, it's negative 2x to the minus 3, which is 12x squared plus 2 over x cubed. So that's option number 3. And yeah. Okay, now for some reason the IB has decided to separate the case of x to the power of n for n being an integer and then for n being a rational number. I don't know why. I think maybe the AI students don't learn it for rational numbers, but in our case it makes no difference. So if I have a function that's defined by x to the power of 4 divided by 3, okay, then I can still apply the same rule. The same rule still applies, it's just that n is no longer an integer. I take down the constant, put it in front, so I have 4 over 3 in front, and I subtract 1. Now, because it's 4 over 3, subtracting 1 is the same as subtracting 3 over 3, so I get x to the 1 over 3. All right, I'm going to give you 10 seconds to start thinking about this, and then I'll solve it. Okay, I think that's enough time. I have this nasty looking square root here, but I can rewrite that using my exponent laws, and I can rewrite this as 4 over x to the power of 2 over 3, and that becomes 4x to the minus 2 over 3. So when I differentiate that, I bring down the 2 over 3 and multiply it by 4, so I'm going to get a negative 8 over 3. I'm going to have x to the power of negative 2 over 3 minus 3 over 3 is negative 8 over 3 x to the negative 5 over 3. Okay, and I see that that is this option over here. Yeah. Let me just double check. I think we could write it as a square root. If you want to turn it back, but this form is perfectly fine as well. Yeah. We also have the derivative of e to the x, and this one is beautifully easy. The derivative of e to the x is just e to the x, and that is one of the things that makes the Euler's number e so special, is that it is the most natural exponent to take, because if I differentiate it, I just get e to the power of x. Okay, and we're going to see something that's similarly interesting for the natural log. It's the best log to differentiate. And HL we'll learn about the derivatives of other exponents. What if it's e to the 3x minus 1? We are going to learn the chain rule in just a second. So I'll answer that question when we go over the chain rule. Okay. Yeah, so super, super easy derivative. Now, also the derivative of sin and cos. Okay, so the derivative of sin is cos. The derivative of cos is negative sin. The derivative of negative sin is negative cos, and the derivative of negative cos is sin. So basically, these are going to loop. It's going to go sin, cos, negative cos, and then back to sin. All right, there's a loop in the derivatives of sine and cosine. And the fact that there's a loop in the derivative of sine and cosine is going to be particularly relevant for HL students because it means that there's going to be all sorts of formulas we can prove for the nth derivatives of functions, and we'll talk about that later. Now, like I said, the derivative of the natural log is also quite nice. If I have ln of x, its derivative is just going to be 1 over x, okay? Other logs base 10 or b in general, not so nice. You have to multiply by some constant in front, and we'll talk about that later for HL students. So that's all well and good. We have these rules for the different common functions that we have, but it's typically not really interesting. You're never going to get a question where you just have to use those alone. There are a couple of rules that we can use to combine derivatives, namely the chain rule, the product rule, and the quotient rule that you need to know to combine derivatives. And the chain rule is basically used when you have a composite function. So when you have one function that is a function of the other. So I have g circle f, sorry, and I want to find its derivative, okay? Well, I'm not going to, spend too much time explaining why, except to say that if you think about a composite function changing, I'm changing x, right, in this composite function, and I'm asking how is the overall function changing? So what you have to bear in mind is that there is one function that is going inside of the other. And the function that's inside is changing with respect to x at some speed, at some rate of change. And the outside function is changing with respect to the inside function also at its own rate. So the outside function has a derivative of its own, okay? And we're just going to say that if I have its derivative, if I plug in f of x, the inside function at that particular value, that's going to tell me how fast the outside function is changing compared to the inside function. But we have to remember that it's not the inside function that we're changing when we take a derivative, it's x. And so I have to ask myself now, how fast is the inside function changing? And I multiply this by the rate of change of the inside function, which is f prime of x. Okay, so just a little bit of intuition about where this formula came from. I'm not going to go into like the detailed proof because we don't have time. Another way that this is often written is if I have dy over dx, I can write that as dg by du times du, and it's not supposed to be dy, it's supposed to be dg, sorry. dg by dx over du by dx. And if you like, it's not mathematically correct, and the fancy mathematicians in universities would probably kill me if I said this, but we can cancel the du's, okay? And you see that I have dg over dx on both sides. It's not strictly speaking a correct thing to do, but for the sake of just building a bit of a mental model, it's not such a terrible heuristic. Okay, so let's do an example. Let's say I have sine of x squared. Well, the derivative of the outside function of sine is cos, okay? And I put the inside function x squared into that, and then I multiply by the derivative of x squared, and the derivative of x squared is 2x, okay? So that's all I did. Now, this version of the formula is in your booklet. Unfortunately, this one is not, and I find this one a lot more intuitive than this dg by du. What you can do if you're looking at that formula and you're stuck and you're like, I don't know how to use that, just say, okay, I have g of u instead of g of f, and say that, okay, I'm going to let u is equal to x squared, and now I have cos of u, and then that my formula says dg by du times du by dx. Well, dg by du is just going to be sine. It's going to be this is supposed to be sine. What am I saying? Sine of u. So dg by du is going to be cos of u, and then I'm going to multiply that by du by dx, which is 2x, and I just plug back in u is equal to x squared, and that's how you could use that formula, even though it's a little bit less clear, I think. Okay, so I'm going to give you 10 seconds to try this example on your own. All right, I think that's enough time. My outside function is sine. and the derivative of sine is cosine. I have cosine of the inside function, which is 3x squared plus 2, and I multiply that by the derivative of the outside function. And the derivative of 3x squared plus 2 is just 6x, because a constant differentiates to 0. So my answer is 6x cos 3x squared plus 2. Okay? 6x cos 3x squared plus 2. All right, 2 more rules to learn, and they're actually the same rule. You can get away with just knowing the product rule if you're smart about it. But if I have a product of 2 functions, let's say they're u and v, then the derivative of u and v is the derivative of u times the function v plus the derivative of v times the function u. Okay, it's in your formula booklet. That's the good news. I have something similar for quotients. If I have u divided by v and I take the derivative, that's equal to u prime v. When I say u prime, I mean the derivative. I'm going to start using that as a bit of a shorthand notation. I have u prime v minus v prime u divided by v squared. Now, here's an example. If f of x is equal to x times the sine of x, then the derivative of f is going to be the derivative of x times sine plus x times the derivative of sine. And that's going to be, the derivative of x is just 1, so I get sine x plus x cos of x. Okay? If I have sine x divided by x, then I can do sine of x prime, the derivative of sine x times x minus x prime sine of x, and sine x prime is cos x, so I have x cos x minus sine x, and I divide in the denominator by v squared, in this case by x squared. Okay, this is in your formula booklet. The one thing I will say is that this one is a sum, so it doesn't matter whether you do u prime v plus v prime u or the other way around, v prime u plus u prime v. Here it does make a difference. If you do v prime u minus u prime v, you're going to get negative. You're going to get the wrong answer. So be very, very careful that the first one that you do the derivative of is the numerator function. The derivative of the numerator times the denominator minus the derivative of the denominator times the numerator. Okay? So yeah, your turn. I'm going to give you, 10 seconds. Okay, I think that's enough time. I'm looking for the derivative of this product of e of x sin of x. So I'm going to use my product formula. I'm going to do u is equal to e to the x and v is equal to sin of x. And then f prime of x is going to be u prime v minus v plus v prime u, sorry. Okay, and my u prime, derivative of e to the x is just e to the x, and v prime, the derivative of sin x is cos of x. And so I get e to the x sin of x plus cos x e to the x. Okay, and you could factor out e to the x if you want, and you would find e to the x times cos x plus sin x. That is this option here. Now, those are all the differentiation rules we need to learn at the standard level, and we're ready to start kind of learning the applications, the way that these are going to show up on exam questions. One of the most common ways is what we call tangent lines, and we talked earlier about tangent lines when we were kind of introducing the notion of the derivative, but the IB is pretty often going to ask you to find the equation of the tangent to a graph, okay? So I have a straight line, mx plus c, and if it's tangent to the graph, a tangent, remember, means that it kisses the function, so it touches the function, and it has the same slope there. So there's 2 conditions. The line and the function have the same y component, so I can say that the function is equal to the line at that point. So f of a is equal to ma plus c, where a is the x coordinate. And they also have the same slope. So f prime of a is equal to m. Using this point slope form of the line, which if you're not familiar with, you can go watch the session on straight lines, I can write y minus f of a is equal to m times x minus a. It's a little bit easier than start writing y is equal to f prime of a x plus c and solving for c, but that will work too. So if you're used to just kind of solving for c by using the y condition, that's also totally fine. I just think it's a bit slower. Okay? When I rearrange it, I get, in general, you don't need to remember this at all, mx minus ma plus f of a. Again, you don't need to remember it. We're going to always be able to derive it in specific examples anyways. So here's a little picture of what that looks like. I have the tangent at a comma f of a, and the equation, again, you don't need to know this. So let's do an example. I have the function f of x is equal to x squared minus x. And I'm looking for the tangent at x is equal to 1. So I find the derivative. I get 2x minus 1 for the derivative, and I plug in 1, and my derivative is going to be f prime of 1 is going to be 1. Okay, so the slope of the line is going to be 1, and I use my point slope form, and I say y minus f of 1 is equal to f prime of 1 times, in brackets, x minus 1. And what I put in here in this minus 1 is the x coordinate that I'm interested in, right? So I do y minus the y coordinate is equal to the slope times x minus the specific x coordinate that I'm looking at, all right? And that gives me the equation y is equal to x minus 1 for my tangent. It's your turn. I'm going to give you 20 seconds to get a head start on me. Okay, I think that's enough time. I have the function x cubed minus x squared. Its derivative is 3x squared minus 2x. Okay, which means that its slope at at 1 is just going to be 3 minus 2 is 1. And I can use the equation y minus f of 1 is equal to m times x minus 1. And f of 1, if I plug it in, is going to give me 0. So I'm just going to have y is equal to, m is just 1, so it's going to be x minus 1 is my answer. X minus 1. So I'm looking at this function, which is the square root of x plus m plus n. And m and n are constants, which means that they're not going to affect the derivative in a particular way. I can just treat them as constants. So I'm going to rewrite f of x using an exponent notation because it's going to be a bit easier. I'm going to write x plus m to the power of 1/2, and that's going to be plus n. Okay? Now, I can use the chain rule, except now the derivative of the inside is just 1, and I can write this is going to be 1/2 of x plus m. If I do 1/2 minus 1, it's going to be minus 1 over 2. And then that's plus, the derivative of n is 0, of the constant is 0. So this just becomes 1 over, I can draw that a bit better, 1 over 2 times the square root of x plus m. So 2 times the square root of x plus m. That's my derivative for part A. Now, in part B, we're told that the second function, g of x is equal to e to the x plus 2n, has a common tangent with f at x is equal to 1. So if I find, sorry, this is f prime of x, g prime of x is just equal to e to the x. And if they have a common tangent, it means two things. It means that f prime of x, f prime of 1, sorry, is equal to g prime of 1. And it also means, and we'll use this later, that f of 1 is equal to g of 1. So let's start with this condition. F prime of 1 is equal to g prime of 1. I can write, well, g prime of 1 is e to the 1, is just e. And on the left-hand side, I have 1 over 2 times the square root, 1 over 2 times the square root of 1 plus m. Square root of 1 plus m. All right. So what I'm going to do is I'm going to now square both sides. And I'm just going to make a bit of space on the screen share so you can see a bit better. Let's fix this. So I'm going to square both sides. I'm going to have 1 over 4 times 1 plus m is equal to e squared. And now what I have to do is I'm going to multiply both sides by 1 plus m. And I'm going to get 1 over 4 is equal to e squared times 1 plus m. Now I can divide both sides by e squared, and I'm going to get 1 over 4 e squared is equal to 1 plus m. And that leads me to the answer m is equal to 1 over 4 e squared minus 1. Okay? So that is the answer to, that's the working to show part B. Now, I know that, and I'm just going to remember the derivatives that I have, which are f prime of x is equal to 1 over 2 square root of x plus m, and g prime of x is equal to e to the x. We shouldn't need them again, but still. And I'm now looking for the value of n, okay? And the value of n I'm going to find by using the fact that the functions are equal at these 2 points. So in particular, f of 1 is equal to g of 1, which means that the square root of 1 plus m plus n is equal to e to the x plus 2n. And I'm going to simplify that. I'm sorry, e to the x is, in this case, e to the 1, which is just e. Now I'm going to simplify the n's to one side, and I'm going to have the square root of 1 plus m is equal to e plus n. Now, I think it's worth isolating e if I can, but I can also remember that we found that m is 1 over 4e squared minus 1. So that means that m plus 1 is just 1 over 4e squared. So if I take the square root of that, it's going to be the square root of this. And so the square root of m plus 1 is, and this is just 1 over 2e. Okay, so 1 over 2e, 1 over 2e minus e is equal to n. And that's a perfectly fine form to leave the answer in. Yeah, I'm perfectly happy with that. 1 over 2e minus e. That's my answer. Okay, next thing I want to talk about are normals to graphs. And normals are somewhat similar to tangents, except that they are perpendicular to the function at a particular point. So let's remember from straight lines that two lines are perpendicular if their slopes multiply to minus 1, which means that the slope of the normal is minus 1 divided by the slope of the tangent, because if the tangent is parallel to the graph and the normal is perpendicular, then they're going to be at right angles to each other. And so the slope of the normal is negative 1 over f prime of a, which is the slope of the derivative at that point. And I can use my point slope form again. I can do y minus f at that point. E is equal to the slope of the normal times x minus the x coordinate that I'm interested in. Okay, and I'll show you an example in a second. If I have f of x is equal to x minus 2x squared, and I'm looking for the normal at x is equal to 2, all right, f prime of x is equal to 1 minus 4x. So f prime of 2 is equal to negative 7. That's the slope of the tangent. The slope of the normal is negative 1 divided by that. So negative 1 divided by negative 7 is 1 over 7. And then I plugged it into my point slope form. I do y minus f of 2 is equal to 1 over 7 times, I do 1 over 7 times x minus 2. And I don't know what all this mess is over here with the 2 minus 2 times 2 squared. What's that doing? That's not supposed to be there. That's already captured on the other side. So ignore that. That's a bit of a silly mistake. And I would get y minus an f of 2 is just going to be, well, 2 minus 2 times 2 squared. That's 2 minus 8 is negative 6. Okay, so then I have y is equal to 1 over 7x. Then I have minus 2 over 7 plus 6 over 7. And it's supposed to be minus 6 over 7, sorry. Minus 6 over 7, and that's going to give me minus 44 over 7. Okay, that is my answer. And why is there a negative there? There should not be a negative. That should be a positive. A couple of typos in these slides in certain places. All right, your turn. I'm going to give you, 15 seconds just to get a head start, and then I'm going to show you the solution. I think that's enough time. Let's start by finding the derivative. F prime of x is equal to 3x squared minus 2. So at x equal to minus 1, I have f prime of minus 1 is equal to 3 times negative 1 squared is just 1. So 3 minus 2 is equal to 1. If I have 1, that means the slope of the normal is going to be minus 1 over 1, which is just minus 1. Now I can use my point slope form, y minus f of minus 1, sorry. Minus 1 is equal to the slope, negative 1 times x minus minus 1. Okay, so f of negative 1, if I do negative 1 cubed, that's negative 1. And then minus 2 times negative 1 is going to be plus 1. So I'm going to have y minus 1 is equal to negative x, and then negative 1 times, this becomes a plus plus over here. So minus 1. That means y is just equal to minus x. That's my answer. Okay, let's go over this. So I have a function, ax plus a plus 2, all in brackets, times e of x. And the first thing we want to do is find f prime of x. So this, I'm going to have to use the chain rule because I have u is equal to ax plus a plus 2, and v is equal to e to the x. So u prime is just going to be a, because it's just the coefficient in front of the x, and everything else goes to 0. And v prime is also going to be e to the x. So I can say the derivative is going to be u prime v plus v prime u, which is going to be a e to the x plus e to the x times ax plus a plus 2. So it's going to be e to the x. The only thing that changes is I have 2a instead of just 1a because I have another one from here. So I have e to the x times ax plus 2a plus 2, right? Plus 2. That is my answer to A. And now, in part B, I'm told that the line y is equal to negative 1 over 3x plus 2 is normal to the curve of y is equal to f of x at x is equal to 0. Okay, so if the slope of the normal is negative 1 over 3, that means the slope of the tangent is negative 1 over that, negative 1 over negative 1 over 3, which is equal to 3. So I can set f prime of x of 0, actually, sorry, f prime of 0, because I'm told the slope is at 0, is equal to 3. And that is e to the 0 times a times 0 plus 2a plus 2. Okay? What does that mean? It means that I have this is equal to this is just 2a plus 2. 2a plus 2 is equal to 3. And so 2a is equal to 1. And so a is equal to 1 over 2. And we have found a. Not so hard of a question there. Now, we're going to talk about the second derivative. And the second derivative is just the derivative of the derivative. I take whatever I found for my derivative, and I take the derivative again. And in this dy notation, I write d squared y by dx squared. And it means the d by dx of dy over dx. I can also write y prime prime. That's an equivalent notation. Quick example, y is equal to 3x squared. That means that y prime is going to be 6x, which means that y prime prime is going to be 6. Another example, if f of x is x cubed minus x, then f prime of x is 3x squared minus 1, which means that the second derivative is f prime prime of x is equal to 6x. Okay? Okay, that's enough time. I'm going to start. I'm going to say u is equal to x squared, and v is equal to e to the x. Okay, that means that u prime is equal to 2x, and v prime is equal to e to the x. So f prime of x is equal to u prime v plus v prime u is equal to 2x e to the x plus x squared e to the x, which is equal to 2x, or I can just write in brackets, e to the x times x squared plus 2x. All right. Now, I take the derivative again, and I do f prime prime of x. Now I'm going to let u be equal to, oh god, u is equal to x squared plus 2x, and v equals e to the x again. So u prime is equal to 2x plus 2, and v prime is equal to e to the x. And f prime prime of x is going to be u prime v. So u prime v is going to be 2x plus 2 e to the x, and then plus uv prime. So plus x squared plus 2x e to the x. And that's going to give me e to the x times x squared plus 4x plus 2. And actually, HL students, if you look at this and you think about taking more and more derivatives, if you take the derivative again, it's going to start to form a pattern. And there's a lot of questions like this that we'll talk about later. But in any case, this is my answer, so let me check it off. E to the x times 2 plus 4x plus x squared, that is this one, yeah. Now, we have to talk about increasing and decreasing regions. So we say that a function is increasing when its derivative is positive, when it's sloping upwards. And we say it's decreasing when it's sloping downwards, okay? And we say that the points at which it is neither increasing nor decreasing are stationary points. So this is f prime equal to 0, f prime less than 0, f prime greater than 0. Okay, let's do an example. If I have f of x is equal to x squared plus 3x, then f prime of x is equal to 2x plus 3. And I can solve when f prime of x is equal to 0. I can do 2x plus 3 equals 0, means x is minus 3 over 2. And because f prime of x is 2x plus 3 is a line sloping like that, it's going to be negative for everything to the left of the root and positive for everything to the right. So f of x is decreasing for x less than 3 over 2. It's stationary at x equals to negative 3 over 2, and it's increasing for x greater than negative 3 over 2. Okay, that's enough time. F of x is equal to x cubed minus 12x means that f prime of x is equal to 3x squared minus 12. Okay, so that is going to be equal to 0. Let's solve 3x squared minus 12 is equal to 0. that means that x squared minus 4 is equal to 0. So x squared is equal to 4, or x is equal to plus or minus 2. Those are my roots. Now, here's the thing. I have a quadratic, 3x squared minus 12, which is concave up, and has a root at minus 2 and at 2. And the question is asking me where it's decreasing, so where the derivative is 0. Okay, this is the derivative. So the derivative is negative between the roots of the quadratic. So it's between negative 2 and 2. That's my answer. Okay, with that said, we can talk about maxima and minima. So stationary points on the graph, the points where the graph becomes horizontal, will sometimes be local maxima or local minima. Now, the way that you can tell if it's a maxima is to look at the second derivative. And when you have a local maxima, it means the function is leveling off, and it's also bending downward, which means the slope is changing from positive to negative. And that means that the second derivative is negative. Okay? You don't always have to check with the second derivative. You can also just plug in values and see that the function changes, but it's more rigorous to use the second derivative. So the function is curving downwards. And similarly, at a minimum, I go from a negative slope to zero slope to positive slope. The function is curving upwards, and I have a positive second derivative. So let's do an example. If I have f of x is equal to x cubed minus 3x squared, then my derivative is f prime of x is equal to 3x squared minus 6x. Okay, I can factor that as 3x times x minus 2. I don't know why I did that, but in any case. And then f prime prime of x, the second derivative, is just 6x minus 6. So if when I have x is equal, f prime of x is equal to 0, when x is equal to 0 or x is equal to 2. So those are the two coordinates of my stationary points, x equals to 0, x equals to 2. And f prime prime of 0 is negative 6, is less than 0, and that therefore corresponds to a maximum because the second derivative is negative. It's curving downwards. Curving downwards means I just passed a maximum. And f prime prime of 2, the other stationary point, that's positive 6, which is greater than 0, and so that corresponds to a local minimum. Okay, so I have a function 2x cubed minus 3x squared, which means its derivative is 6x squared minus 6x, which means its second derivative is going to be 12x minus 6. Now, when is that equal to 0? Oh, sorry, when is this equal to 0? So if that's my derivative, I can write that as 6x times x minus 1. So in other words, I have stationary points at x equals to 0 or x equals to 1. That's when the first derivative is 0. Now f prime prime of 0 is equal to 12 times 0 minus 6 is negative 6 is less than 0. So that's a max. And f prime prime of 1 is equal to 12 minus 6 is 6, and that's greater than 0, so that's a minimum. Okay? Minimum. So I have a, and the question wants me to find the coordinate, so I have to plug this back into the original function. F of 0 is equal to 0, and f of 1 is equal to minus 1. And so I'm going to have my local maximum at 0, 0. So local max at 0, 0. And my local min is going to be at 1, minus 1. All right, so 1, minus 1. Okay, so we have another IB style problem here. I'm going to give you 4 minutes to get a head start over me in case you want to try this on your own, and then I will go over the solution with you. All right, let's go over this. So I'm going to make a little picture because it's going to help us draw this. But I have a straight line with a slope of m, which is negative. So I have a negative slope, and it passes through the point 3, 5. So the point 3, 5, I'm going to put, it's approximately here, let's say. 3, 5 is approximately there. Maybe I'll put it a bit lower. 3, 5, and I have a line that goes through that point. Maybe I'll do it like this. Okay? And let's say that the y-intercept is b and the x-intercept is a, just for now, okay? I know that b over a is going to be equal to negative of the slope. So if I should do negative b over a, I should get the same thing as the slope because I had my rise over run. My rise is negative b, my run is a. Okay, so that is one thing. I also know that the line passes through 3, 5, which means that I can say if my line is going to be equal to y is equal to mx plus b, b is the y-intercept, remember, then I can say 5 is equal to 3m plus b, which tells me that b is equal to 5 minus 3m. And that's helpful because now I can say that I have 3m minus 5 over a is equal to m. And so a is equal to, I just multiply both sides by a and divide by m, 3m minus 5 over m. Okay, those are my two answers for part A. I have 5 minus 3m for B, and 3m minus 5 over m for A. Okay, so let me make some room. So now we want to show that the area of the triangle formed by the line and the coordinate axes is that equation. So, I mean, the good news is that it's a triangle, so we can use base times height, right? And I know, hang on, I just want to make sure of something because I feel like there is something wrong here. It should be minus m. So people do think it should be minus m. Oh, yes, it's minus m. Sorry, it is minus m. It's minus m. So this makes this plus and that plus. I knew there was a sign error somewhere. So that is helpful. So the area of this triangle is just half of base times height. Half base times height. And the base I can say is b, and the base is going to be a, and the height is going to be b. That's probably a bit backwards, but whatever. And so I can say this is half of, and I'm going to have 3m plus 5 squared over m. Okay, make a bit of room. I expand all of this. I get 9m squared plus 30m plus 25 all over 2m. Now, that's the expression for B, so that's that. And in part C, I'm asked to find the minimum possible area of the triangle. So I have this function for the area in terms of m, and I want to find when it's minimum. First, I need to find when it's stationary, and hopefully that will correspond to a minimum. Okay, so I could use the quotient rule to take this derivative. I don't want to do it. I don't want to take a prime of m using the quotient rule. Instead, what I'm going to do is I'm first just going to divide every term by m, and I'm going to get, I can write this as 9m over 2. So I'm going to get 9m over 2, or half of 9m plus 30 over 2 is 15, plus 25 over m. And that's a lot simpler because now I just have a bunch of terms separately. When I take its derivative, a prime of m, the half just stays in front. The 9m becomes 9, 15 goes to 0, and 25 over m becomes negative 25 over m squared. Okay, and that is all equal to 0. Then this is supposed to be equal to 0, so 9 is supposed to be equal to 25 over m squared. All right, and so m squared is equal to 25 over 9, which means that m technically is plus or minus 5 over 3. But the question tells us that the slope is positive, that I have m greater than 0, so I have m is equal to negative 5 over 3. Now, I could check if this is a local maximum, a local minimum. I don't actually have to because I only found one of them. So the question doesn't ask me to justify that it's a minimum. I also can tell by taking this line that if I drew a straight line that was parallel to the x-axis, if I let m go to 0, then the area of the triangle would become infinite. So actually, I'm safe in assuming that this is going to be the coordinate of the minimum. And I plug that back into my expression for the area. And I do 9 times negative 5 over 3 squared plus 30 times negative 5 over 3. It might be out of room this. I'm going to do plus 25 and all of that over this fraction, 2 times negative 5 over 3. Okay, and if I simplify that, it's a bit of a mess, but I'm going to have 9 times 25 over 9, and then 30 times 5 over negative 5 over 3. The 30 divided by 3 makes 10, so then it's going to be minus 50 plus 25 all over, why is that giving me 0? Hang on. This is supposed to be, oh, again, m is positive. I don't know why I said negative. We took the positive one because m was greater than 0, okay? Took the positive one, so I put in the positive, positive, and so I still have 25 over 9, it's just that this is 50. And so I can say that this is all over, we said it was 2 times 5 over 3, so 10 over 3. 10 over 3. And so that gives me 100 over 10 over 3. which is 3 times 100 over 10, which is 30. So that is the minimum possible area. Okay, now we're going to talk about inflection points. And inflection points are the places where the second derivative changes sign. So it has a 0 and it changes sign. So I want you to look at this graph here, which shows in a solid line, f of x, and in the dotted line, it shows f prime prime of x, the second derivative. So notice that when the second derivative crosses the x-axis, you get a change in concavity, which means the function was bending down. Now it's curving up. Okay, so there's a change in the curvature of the function, if you will. I also want you to notice that even though f prime prime of x is 0 here, there's no inflection point here. It's bending up, and then it's not bending at all, and then it bends up again, because the f prime prime of x has a 0, but it doesn't cross the x-axis. It touches and it goes back up. Okay, so specifically, you have an inflection point when the second derivative changes sign. Now, I've never seen an example in the IB where you have a function that has a 0 for its second derivative, but it doesn't cross the axis, because that would be really, really tricky to give you that. But if there was ever a graphical question where they showed you the second derivative, I would want to make sure that you guys knew that. Okay, so here's an example. Let's say I have the function x cubed plus x, whose derivative is 3x squared plus 1, and therefore second derivative is 6x. I have f prime prime of x is equal to 0 when x is equal to 0. And I can tell by looking at 6x that it actually does change sign. So I have an inflection point at x is equal to 0. When you say I don't get that, someone says I don't get that, I can go over it one more time. But inflection points in general happen when the second derivative is 0. But the second condition is that the second derivative actually has to change, because what you see here is that even though the second derivative is 0, I can draw a straight line that touches the graph, but it doesn't cross it again. You can't do that at an inflection point. When you draw the tangent, it has to cross the graph somewhere else. And that's because the curvature of the function is going to change. It starts bending in the other direction. Okay, so it was concave down, and now it became concave up. And I'm going to show you how to visualize concavity in a second. But the thing to focus on is that if the second derivative does not change sign, if it has like a double root, then there's not going to be an inflection point. And again, I haven't seen this show up in a question, but for the sake of just making sure that you're aware of it, I wanted to mention it. All right, that is enough time. So I have y is equal to x cubed plus x squared. So y prime is equal to 3x squared plus 2x, or y prime prime is equal to 6x plus 2. That is equal to 0 when 6x is equal to minus 2. So x is equal to negative 1 over 3. Okay, and 6x plus 2 is a line that is going straight up, so it is going to change sign. So I'm going to have an inflection point at x is equal to minus 1 over 3. What is the y coordinate? So I do y of negative 1 over 3, and I'm going to find, so that cube is going to be negative 1 over 27 plus 1 over 9. So that's going to be 1 over 9 is 3 over 27. So 3 minus 1 over 27 is 2 over 27. So minus 1 over 3 and 2 over 27 is my answer. Now I have a calculator question, which is to find the inflection point on the curve of y is equal to x e to the 6x all to the power of 8x cubed. This is a nasty function. I have a product rule on the inside, chain rule on the outside. It's a lot. I don't actually want to do this derivative by hand. I definitely don't want to do a second derivative by hand. What I can do is realize that if this is the curve, if I were to find the derivative on the calculator, then the derivative would look something like this. Okay, I don't know exactly where. Let's say that and I'm looking for the zeros of the second derivative. So I'm looking for where f prime prime of x is equal to 0. But f prime prime of x, y, the second derivative, is equal to, it's the derivative of the first derivative. Okay, it's the derivative of the first derivative. And so when y prime prime is 0 is when the first derivative has stationary points. So what I can do on my calculator is graph the first derivative and look for the maxima or minima of the first derivative. So let me show you how I would do that on my calculator. So let me just remember the function that I had, and I will clear all of this stuff out. I had x e to the 6x all to the power of 8x cubed. So 8 second e to the power of 6x all to the power of double checking. Yeah, 8. No, sorry, x, not 8. X e to the 6x to the power of 8x cubed. So x e to the 6x all to the power of 8x cubed to the power of 3. Okay, that is what I have. And so I'm just double checking if that is the curve that I have indeed. Yes, that's perfect. Perfect. So that is the function that I have. I don't need to graph it, so I'm just going to go over the equal. I'm going to hit enter, so I don't need to graph that one. Then what I can do is I can go math. I can go to this number 8 n deriv, and I can do d by dx of, and I'm not going to retype it again. I'm just going to actually go second, or sorry, not second. I'm just going to go vars, y vars function, and input y1 into here. It's going to take the derivative of y1, and I put x equals to x in here. And I'm going to do a window of negative 5 to 5. And well, I'll do like negative 20 to 20 for the derivative. Why not? It's probably a good bet. All right, let's graph. Okay, so maybe that wasn't a big enough window. Maybe I need to zoom out my window. Let's change the window then. Window from that to, or maybe I need to zoom in the window. Let's see. Let me do -1 now. -1 to 1 and graph that. I can't really see anything, so I'm going to zoom in the, it looks like there is a stationary point there. I just need to find it. So now I'm going to do -1 up to 1 here. There it is. Now I find my stationary point on the original function. So now I go second, calc. I'm going to find, there's a minimum there, so let's go find the minimum. Let's put in our left bound here, our right bound here, and we'll run it, and we'll find x is equal to 0.1118 or 0.112 when we round it, okay? So 0.112. Now to find the y coordinate, what I can do is I can remember I have 0.112, and what I should have done actually, I should have graphed this at the same time, 0.112, because then I could have gone to the minimum. I need to make my window a little bit bigger, like that, y-max, so I can still see it. And I'm going to go now, I'm going to go second calc value. I'm going to go on to 0.112 or 0.1118, I think it was exactly. And on the blue curve, on the original function, that corresponds to 0.983. So that is the coordinate of the inflection point. You can actually see that inflection point right there, kind of, if you zoomed in. So my answer now, if I go back, is going to be 0.112 and 0.983, okay? Now, I'm only showing you this because, again, the IB doesn't require you to know how to do this, but sometimes on a paper 2, they will ask you to find the coordinates of the inflection point, and there'll be like 5 points because you have to find a second derivative, and there's a lot of stuff to do. But if you're really smart with your calculator, you can actually skip all of that, and you just say, explain what in this case, because you're doing something very tricky on your calculator, explain that you graphed the first derivative, and you found the maximum or minimum of the first derivative. Just make sure you explain what you did, and you'll get the full points. A lot faster than having to do nasty derivatives by hand. Now, I promised I would explain concavity a little bit better, and concavity relates to the second derivative. When the second derivative is positive, the function is concave up, and when the second derivative is negative, the function is concave down. You can see that in a picture here, which shows you the concavity as regions where the curve is kind of bending up or bending down. And I like to imagine this as catching rainwater, sort of uh, um, like making pools of water on the function by imagining letting like water fall onto the function. When the function is concave up, you're going to get a pool. You're going to get a pool upwards, and when the function is concave down, you're going to get a pool downwards. I don't know, just the way that I visualize this. I don't know if it's helpful to you, but maybe this picture is valuable. Okay, so I'll let you stare at it for 5 seconds, and then we'll continue. Okay, now this is a tricky little subject, and this looks like a mess, so I'm going to explain it as clearly as I can. You have to know how the graphs of f prime, and f prime relate to each other. So I've drawn in this solid line here the graph of f. In this dashed line is the graph of f prime, and in this dotted line is the graph of the second derivative. I want you to notice a few things. The maximum on the graph of f of x, the stationary point, corresponds to a 0 on the graph of f prime. We know that. A stationary point has a first derivative of 0. Same for this one. It goes through 0 here, right? What else do I notice? I notice that the inflection point on the graph of f matches the 0 of the second derivative. We also know that. That's fine. I also noticed that the minimum, or the stationary point on f prime, corresponds to the 0 on f prime prime, okay? And I also can tell by looking at the signs of these various things that this has a stationary point here, and because the second derivative is negative, that's going to be a maxima, and over here the second derivative is positive, and that's why this is a minimum, okay? And being able to sketch the first derivative or the second derivative using a function is very, very valuable and powerful, and sometimes you could be asked to do that. It's not very common. So here is a simple exercise for you to do. I'm going to give you 10, 15 seconds to think about it, and then I'm going to explain how you would do this. All right, so this graph shows me the graph of the derivative f prime of x, and I know that I have a minimum and maximum when the first derivative is positive, okay, when I have stationary points. And in particular, I have a maximum when the second derivative is negative, when the function is bending down. The second derivative is the slope of the first derivative, okay? And if I'm looking for a minimum is when the second derivative is positive, when the slope of the first derivative is positive. So the slope of that line that I just drew is f prime prime of 1. And this slope over here is f prime prime of minus 3. Okay? I notice that f prime prime of 1 is positive, and that corresponds to a root at f prime of x. So the minimum is going to be here at x is equal to 1. So x equals to 1 is the root, is the minimum. Now, the maximum is when I have an x-intercept for f prime of x, and the second derivative is negative, which is here. The slope of the derivative is negative, so it's at minus 3. Now, I don't know why I forgot to put multiple choice options here. Sorry about that. But we can still answer this question. We just won't have MCQ. The graph of f prime prime of x is shown below. And I want to find the x-coordinates of all the inflection points on the curve of y is equal to f of x. I'm going to give you 10 seconds to think about that. Okay, so this graph shows me the second derivative. And I know that inflection points on the curve of f happen when the second derivative is 0 and changes sign. So in particular, this minus 3 comma 0 is not actually an inflection point because the second derivative does not change sign there. It does change sign at 0, and it does change sign at 1. So the x-coordinates are 0 and 1. Okay? Now, IB style question. This one has not really shown up on past papers before, but I think it could. They could always add this at any point in time, and it really will solidify your understanding of derivatives to work on this. So I'm going to give you 3 minutes to get a head start, and then I'm going to solve it. Okay, what do I have? I have this curve showing the first derivative of a function, and part A wants me to write down the x-coordinate of the local minima. So I have a local minima when f prime of x is equal to 0 and f prime prime of x is greater than 0. So f prime of x is equal to 0 here and here. And I'm looking for the one where the slope is f prime is greater than 0. So that is going to be here at 2 when it changes from negative to plus, okay? So negative to plus is the answer, and that gives me x is equal to 2. Okay, x is equal to 2. And then in AII, I need to find the intervals on which f of x is decreasing. So f of x is going to be decreasing when, let me just make some space here. F of x is decreasing when f prime of x is less than 0, which I can see is this interval here. So it's negative 1 less than x less than 2. That's the answer for AII. Okay? Now, we want to determine the coordinates of the zeros of f prime prime of x. So a 0 of f prime prime of x is a stationary point on f prime of x. So I'm going to have 1 at minus 3 comma 0, because a 0 has a y coordinate of 0. So I have minus 3 comma 0, And the other one is going to be 1 over 4 comma 0, because I have another stationary point on f prime at 1 over 4. So 1 over 4 comma 0. Those are my answers. Okay. And finally, we want to find the equation to the normal of the curve at x is equal to 1 over 4, giving your answer in the form y is equal to mx plus c. And I am told that f of 4 is equal to f prime of 4. Okay, so what is f prime of, f of 1 over 4 is f prime of 1 over 4. So f prime of 1 over 4, I can see is equal to negative 9. So that means f of 1 over 4 is also equal to negative 9. Now, using my point slope form, that means that this is the m of the tangent, so we're not quite there yet. That means that m of the normal is equal to 1 over 9. That means in point slope form that y minus negative 9 is equal to 1 over 9 times x minus 1 over 4. Let's expand that. I have y is equal to 1 over 9 x minus 1 over 36 minus 9. Okay, and 9, if I put it over 36, oof, that's a bit annoying, but I can do it. And over 36, that is going to give me 360 minus 36 is 324. So I have 1 over 9 x minus 1 minus 324 over 36 is equal to 1 over 9x. That's plus actually, minus 325 over 36. And if you'd left it in this form, we would probably also get the points, okay? So don't stress too much about that. Okay, so I have the function f of x is equal to a to the power of, oh no, wait, hang on, this is higher level. This is HL because, yeah, sorry, SL students, you guys don't know the derivatives that you need to solve this. That's a mess up on my part. I shouldn't have showed you this. I'm sorry, guys. Oopsies. You can't even find these derivatives. They're just, or actually, hang on, is that true? What am I saying? You don't know how to find the derivative of this on its own, nor of this on its own, but if you're composing them, then you actually do know how to find their derivatives. Oops, okay. So I was scared for a sec that I made a big mistake. We do know how to solve this. So I have f of g of x is equal to f of 4 log base a squared of x. And it looks like a bit of a mess, but it's okay because f is a to the power of that. So I have that's equal to a to the power of 4 log base a squared of x plus a half. Okay, and that is a to the half times a to the log base a squared of x to the power of 4. Okay, and now we are getting pretty close. I can say that that is, I need to change log base a squared of x to the 4 into log base a by using log base a of x to the 4 over log base a of a squared, which is half of log base a of x to the 4. Okay, so what does this become? This all becomes equals to root of a times a to the half of log base a of x to the 4, or in other words, root a times a to the log base a of x squared. But now, a to the power of log base a is just whatever goes inside the log, so this becomes root a of x squared, root a times x squared, as desired. So that answers part A. Check if there are any questions about that. No, okay. Now, we're considering the function h of x, and the following table shows h and h prime of x for some values of x. Oh my god, and we are considering a function which is f of g of h of x. Oh my god, that's disgusting. But I can write this as f of g of h of x. Okay? And I know what f of g is. We just found that's the square root of a x squared. It's just the square root of a times x squared, so times h squared of x. And that means when I take the derivative, I'm going to get the root of a times 2h of x times h prime of x. Okay? That's how I actually do this. And then u prime of 0 is equal to root of a times 2 times h of 0 is 2, so 2 times 2, and then h prime of 0 is 1 over 2. So this all simplifies to 2 root of a, and that is supposed to be equal to 3. Now I can square both sides and say 4a is equal to, root 3. 4a is equal to 3, and so a is equal to 3 over 4. That is the answer, okay? Apologies for the mix-up there. All right, a is equal to 3 over 4. Let me put that to the side here. A is equal to 3 over 4. All right, and we found that. Now we're trying to find the equation of the line tangent to the graph of u of x at the point x is equal to 1. Okay, so remember, u of x was equal to root of a, h squared of x, and its derivative was u prime of x is equal to 2 root a, h of x, h prime of x. Okay, and so u prime of 1 is equal to 2 root a, and h of 1 is root a, so that times root a again, and then times h prime of x is 1 over 3. So h prime of 1 is 1 over 3, so times 1 over 3. And this becomes 2a squared over 3. And I know that a is 3 over 4, so this becomes 2 times 9 over 16 over 3, which is 9 over 8 over 3. That is 3 over 8. Okay, so that gives me the slope of the tangent. The slope of the tangent is m is equal to 3 over 8. All right, that is the first thing. And of course, I am saying something silly again. It's not a squared. It's the square root of a squared, which is just a. This is just 3 over 4. And so I have 3 over 2 over 3 is 1 over 2. So the slope of the tangent is 1 over 2. All right. Now, slope of the tangent is 1 over 2. I can use my point slope form and say y minus u, in this case, u of 1, is equal to m times x minus 1. Okay, and u of 1 is, if I plug it in, it's going to be u of 1 is equal to root of a, so root a times h of x squared, and h of x squared is itself is a, so it's root of a times a. So this is going to be a to the power of 3 over 2, and root of a, since we found a is 3 over 4, this becomes root 3 over 2 times 3 over 4, or 3 root 3 over 8. Okay, so now this becomes y minus 3 root 3 over 8 is equal to, and the slope was 1/2, so 1/2 of x, so I can say just 1/2 of x minus 1/2. Okay, and now I can simplify that to y is equal to half of x, and then I'm going to have plus 3 root 3 over 8, and if I put 1 over 2 over 8, that's minus 4 over 8. That is my final answer. All right, that was everything for the SL students. So I'm gonna keep going now with the HL content. We have a couple of derivative rules to learn, then we have a couple of extra applications to learn, and then we're gonna be done. We have about an hour left, so I think we're doing perfectly on time. Somehow this actually worked out. All right, so the derivative of tan. The derivative of tan is sec squared of x. Okay, I mean, it's in your formula booklet, whatever. You should also know the nth derivative of a function is just the derivative of the derivative of the derivative n times. And we're going to go over more examples of that in a second and when that's useful. But we use the notation f bracket n of x. And I write d to the n of y over dx to the n, right? That's just notation. And I don't know why tan x I wanted to do a bit later. I'll come back to it. So now we have an example of a proof by induction using derivatives. So I have f of x is equal to 1 plus 4x to the minus 1 over 2. Therefore, f prime of x is going to be equal to negative 1 over 2, 1 plus 4x to the minus 3 over 2 times the derivative of the inside, which is 4. So it's going to be negative 2 times 1 plus 4x to the minus 3 over 2. Now, I'm going to put that off to the side. F prime of x is equal to negative 2 times 1 plus 4x to the minus 3 over 2. And I'm going to start erasing this. And in part B, we're trying to prove by induction that the nth derivative, fn of x, is equal to minus 1 to the n times 2n factorial over n factorial times 1 plus 4x to the power of negative n minus a half. And that looks disgusting. It is pretty disgusting. We're going to take it step by step. So as usual with a proof by induction, I start with my base case. All right, base case, f of 1 of x, the formula tells me is negative 1 to the 1 times 2 factorial over 1 factorial times 1 plus 4x to the negative 3 over 2, which is equal to negative 2, 1 plus 4x to the minus 3 over 2. And that matches what I found f prime of x from A. So true for n is equal to 1. Now, we're going to zoom in and we're going to do, oh, hang on, I have something, never mind. We're going to do the assumption. And I'm going to try and organize this as much as I can because we have very limited space. And hopefully I can fit everything in today. So let's do a divider there, separate that out. And now we'll do the assumption. Okay, so assumption. Assumption for n is equal to k. Assume that I have fk of x is equal to negative 1 to the k times 2k factorial over k factorial times 1 plus 4x to the minus k minus 1 over 2. Now, what do I have to do to prove that I want to prove that it's true for k plus 1. So now we want to prove true for n is equal to k plus 1. All right, so how am I going to do that? What I'm going to do, and you always do with these induction with derivatives questions, is you take the derivative of your assumption. So I say f k plus 1 of x is equal to d by dx. So I'm just going to take out all the constants first, minus 1 to the k, 2k factorial, because these are all constants with respect to x, times d by dx of 1 plus 4x to the minus k minus 1 over 2. Okay, there's no way I'm going to have enough room for this, but I'm going to try everything in my power to make it fit. We'll see what happens. Okay, what I'm going to do is I'm just going to make a line here and win some space up here because we're going to need it. So let's start by simplifying as much as I can. Let's go up here, and I'm going to get still negative 1 to the k, 2k factorial over k factorial. And then I'm going to have d by dx of that. So I'm going to bring down the power. What am I going to have? I'm going to have negative k minus 1 over 2 times 1 plus 4x to the power of negative k now minus 3 over 2 because I've subtracted 1 times the derivative of the inside, which is 4x. Okay? And then what I can do, and not 4x, just 4. Sorry, just 4. What I'm going to do is I'm going to rewrite this now. Negative 1 to the k times 2k factorial over k factorial. I'm going to bring that one of the 2's from the 4, because 4 is 2 times 2, into this k minus half. I'm going to write it as 2k minus 1. Okay, 2k minus 1. Now, let's be careful with our next steps. I want to make sure I have everything right so far. 2k minus 1 times 2. So because I multiplied this by 2. I'm sorry, 2k plus 1, sorry. 2k plus 1 times 2 times 1 plus 4x to the negative k minus 3 over 2. That's a good question. Good catch. It is supposed to be negative 2k plus 1. I hope that answers the question. All right, and that is helpful because now I can take this minus here and I can put that in the minus 1 to the power of k, and that's going to give me minus 1 to the k plus 1 times, and now I have 2k plus 1 times 2k factorial is 2k plus 1 factorial. Okay. Now what I want, by the way, if I have k is equal to n is equal to k plus 1, I want 2k plus 2 factorial. So what I'm going to do is I'm going to write, I'm going to add up here what I want, which is a 2k plus 2, and I'm just going to cancel it out in the denominator. I'm going to, because I can't just multiply it in because I want it, so I'm going to write k factorial times 2k plus 2, right? And that's being multiplied by 2, and then by 1 plus 4x to the negative k minus 3 over 2. All right. And we are getting there. It is definitely messy, though. I probably could have been slightly more efficient. What I'm going to do for this last step is I'm just going to go up to the top here. And when you're writing this on paper and you guys have enough space, it's not good to be jumping all over the page because it makes it harder for you to follow. It makes it harder for the examiner to follow. On my iPad, I kind of don't have a choice. I did try and find a better solution for this, but there really isn't many good solutions for screen sharing this stuff. Okay, so the next step is I'm going to take this 2 and multiply it by the 2k. Well, I have a 2k plus 2 in the denominator and a 2 in the numerator, so I can cancel that and say the 2k plus 2 in the denominator becomes k plus 1. So now all of a sudden in the numerator, I have 2k plus 2 factorial. Let's not forget that I have minus 1 to the k plus 1 in front. And that is being divided by, now I have k factorial times k plus 1. That's k plus 1 factorial. And then that's times 1 plus 4x. Now I'm going to write negative k minus 3 over 2 as negative k plus 1 minus 1 over 2. And that is the statement for n is equal to k plus 1. So the statement is true. Is true for n is equal to k plus 1. Let me check. I think there's a Q&A. How do we avoid messing up the algebra? So good question. How do you avoid messing up the algebra? A lot of it is experience, especially when you're working with these factorials. Part of it is being really, really good with factorials. And what I would kind of recommend you do in general, the way we approach helping students avoid making algebraic or silly mistakes on the website is to use the concept quizzes. So if you go to, that's not what I wanted. I wanted to open it somewhere else. If you go to like Math HL, let me just clear my screen for a sec, and you go to the concept quizzes, you can basically take a quiz for each of the different units, and it'll give you a score over time. And these are basically a race against the clock to go as fast as you can. And these practice your accuracy and your speed under pressure, under time pressure, which is usually what leads to mistakes on the exam. It's pretty new. This is like 3 days old. But yes, you can try every topic and you can see your score in every topic and also your total score by a larger topic over time. All right, so hopefully that is fun. But in general, I would say it takes a certain amount of strategy. So in this case, as soon as I have one of these questions and I'm dealing with factorials, I know I need to slow down and take a bit of a breath. And I need to always be looking for what am I trying to get to and how can I move in that direction slowly. It's also perfectly fine, by the way, once you get to like a step like this, if you want to just take that part that's d by dx, if you want to separate that out and go somewhere else with it and just simplify that and then bring it back, that's also fine. So you don't have to write everything every time. Mostly, though, it's about the biggest reason people make silly mistakes is because they're thinking about the next step when they're thinking about what they're currently doing. So what happens to me is I'll be thinking about the next step and I'll be realizing, oh, that 3 over 2 is going to cancel with that 2, and it's just going to give me 3. And if I was trying to write 4, all of a sudden I'll write 3 because I was thinking about that 3. So you have to be hyper-focused on the task that is currently happening, the step that you're currently doing. And if you want to think about the direction to go, pause, stop writing, think about where you want to go, but don't think about your strategy at the same time as you're writing, or you're going to accidentally write down your strategy in the wrong place. And then you're going to have big problems. And it's very, very difficult to catch this stuff. It's even more difficult to catch if you have bad handwriting and bad organization. So this is pretty bad on the iPad, I know. I made a lot of silly mistakes in high school until my teacher really forced me to write everything really nicely. I was basically not allowed to submit any work unless I drew all my fractions with a ruler. Every question was separated with a new line, and I started to treat my submissions and everything that I wrote kind of like it was like a piece of art. It had to be really, really nice to look at. And it wasn't just a useless exercise. It made it so that first of all, I was thinking a lot more about everything that I wrote and making sure that it was correct and well presented. And it meant that if there was a mistake, I could see the mistake a lot more quickly because it jumped out at me. When I have giant, messes all over the page, it's very, very difficult to see when I have something that's incorrect. But if everything is uniform and standardized and nice and pretty, the mistakes will jump out at you a lot more. So that is my kind of advice for people who make a lot of algebraic mistakes. And yeah, that plus doing a lot of easy practice, not just practice problems, because if you get the ideas, you get the ideas, but you need to be so good at the basics that the basics are never the issue. And the way to get good at the basics is to do our concept quizzes. So I don't know why I did it in this order. I wanted to quickly show you the derivative of tan x. I wanted to show you this slide first. So derivative of tan x is the secant squared, all right? And the derivative of the inverse trig functions, derivative of arc sine is 1 over square root of 1 minus x squared. Derivative of arc cos is negative of that. And derivative of arc tan is 1 over 1 plus x squared. These are in your formula booklet, and they don't show up too often in differentiation. They're actually more commonly used in integration when you want to integrate something of this form. And we will talk about that tomorrow when we do integrals. Okay, the derivatives of reciprocal trig functions, derivative of secant is secant tan, derivative of cosecant is negative cosecant cotangent, and the derivative of the cotangent is negative cosecant squared. All in your formula booklet. I do not remember these by heart. I have to check them every time. The SL ones I remember by heart because they're so easy. E to the x, sin x, cos x, whatever. All the others, no, I don't remember them. You need to know the derivatives of f of x is equal to a to the x. It's kind of similar to e to the x. It gives f prime of x is equal to a to the x, but now times ln of a in front. And notice that if a is equal to e, then I just have e to the x ln of e, and ln of e is 1, so that's e to the x. So it simplifies to the case that we already know when we have that. And the last one we need to know is if f of x is equal to log base a of x, then f prime of x is equal to 1 over x with an ln of a here in the denominator. Okay, I'm going to give you a second to do this one. Now, the derivative of tan of 4x squared minus x. Okay, so I have to use the chain rule here. I know that the derivative of tan, if I have f of x is equal to tan x, then its derivative is secant squared of x. So the derivative I'm going to have here is going to be secant squared of 4x squared minus x times the derivative of 4x squared minus x, which is equal to sec squared of 4x squared minus x, minus x. See, that was just an example of me making a mistake by thinking about what was coming next, not thinking about what I was doing. I wrote 8 because I was thinking about what was happening next, because I was thinking 8x minus 1. Okay? And that is option number 3. Now, a very sort of common IB differentiation question at the higher level is using implicit derivatives, which means I don't have an equation for y in terms of x, but I have a relation between x and y that defines a curve. But I can just do the derivative of both sides and use the chain rule to simplify that. So let's say I have x squared y is equal to 3x plus 1. I take the derivative of both sides, and I get 2xy plus x squared times the derivative of y is equal to 3. And if I isolate y prime, I get 3 minus 2xy over x squared. Now, sometimes the IB will ask you to give an expression for the derivative just in terms of x, in which case you can find y from the original equation. If I have x squared y is equal to 3x plus 1, I find y is equal to 3x plus 1 over x squared, and I plug that back in, and that would lead me to y is equal to negative 3x plus 2 over x squared. Next important thing to talk about are related rates. So related rates are questions where you have one variable that depends on another variable that depends on a fundamental variable like time or distance or something like that. So it's kind of like the chain rule, except that you're going to be not just finding the final derivative, but kind of working with weird rates of change in between and how they relate to each other. So let's start with a simple example, which is with volumes. It happens pretty commonly on IB. And let's say I have the radius of a sphere is changing at a rate of dr by dt is equal to 0.2 meters per second. And we want to find the rate of change in the volume of the sphere when r is equal to 3. So let's say I have the volume is 4 over 3 pi r cubed. That's my formula. So using the chain rule, I can write dv by dt is equal to dv over dr times dr over dt. And dv over dr, I can take that derivative. I bring down the 3. It becomes 4 pi r squared. And that is being multiplied by dr by dt. And I know that dr by dt is equal to 0.2 and r is equal to 3, so I plug those in. I get 4 pi times 3 squared times 0.2. That's 9 pi over 5, and my units are meters cubed per second. It's very important that you put the units or you won't get the answer point. Now, another kind of related rate that shows up a lot is with implicit differentiation, where you're given a curve like 2xy is equal to e to the x minus 1, and you're given that dx by dt is equal to 3 when x is equal to 1, and you have to find dy by dt. So again, we differentiate both sides. I get 2x times dy by dt plus 2y times dx by dt is equal to dx by dt times e to the x minus 1. I plug in x is equal to 1 and dx by dt is equal to 3. I get 2 times 1 times dy by dt is equal to 2y times 3. And that's supposed to be equal to, on the right-hand side, I just have 3 times e to the power of 0. That should be 3. I isolate dy by dt, and I get 3 minus 6y over 2. But we want a number. So how do I find y? I take the original curve at x is equal to 1, and I have 2 times y is equal to e to the 0 is 1. That means y is equal to 1/2 when x is equal to 1. I plug that in, and I get dy by dt is equal to 0. Another kind of related rates is the distance between 2 points. If I have 2 points, I can say the distance between them is the x distance squared plus the y distance squared. So I can say that this is L squared is equal to x squared plus y squared. I take the derivative, and I find that 2L times dl dt is equal to 2x dx dt plus 2y dy dt. And if I'm told that dx dt is equal to 0.3 and dy dt is equal to 0.1, then I have and I'm told that xy is 3 meters, 4 meters. I can plug everything in. I find that L is equal to 5 using just Pythagoras, and then 2 times 5 times the rate of change in L is equal to 2 times x, so 3, so 6 times 0.3 plus 2 times 4 is 8, so 8 times the rate of change of y is 0.1, and that gives me 10 dl by dt is equal to 2.6, so dl by dt is equal to 0.26. So the actual change in the distance is somewhere between the x and the y. That's kind of my takeaway here. These are the hardest ones, I think, but also I would say the most common out of all of them are the angle-related rates. You'll have a right-angle triangle or maybe some other non-right-angle triangle that's set up in such a way that you have this relationship between theta and x. So in this picture, I have theta is opposite x, and there's an adjacent side of 3, so I can say that tan of theta is equal to x. So theta is equal to arctan of x over 3. All right, so tan of theta is x over 3. And if I differentiate both sides, I get d theta by dx is equal to 1 over 3 plus x squared. That's just using the formula that's in my booklet with the chain rule, sort of. So multiplying everything by 1 over 3, okay? Now, I know that dx by dt is equal to 0.1 and when x is equal to 3, and I'm trying to find d theta by dt. Using the chain rule, d theta by dt is d theta by dx times dx by dt. So that's going to give me 1 over 3 plus 3 squared, using this formula here, 3 plus 3 squared, times 0.1. That gives me 1 over 300, and my units are radians per second, okay? Okay, time is up. Let's go over this. So I have a curve x squared y plus e to the y is equal to x. If I differentiate both sides, I'm going to get 2x y prime plus, sorry, not 2x, I'm going to get 2xy plus x squared y prime. That's using the chain rule on this. Sorry, the product rule on that. Then plus, I'm going to get y prime e to the y using the chain rule. That's equal to 1, taking the derivative of the right-hand side. Now, if I collect everything in y prime, I'm going to get x squared plus e to the y. If I move everything else to the other side, I have 1 minus 2xy. So in other words, y prime is equal to 1 minus 2xy over x squared plus e to the y. Okay, that is part A. Now in part B, we are trying to find the rate at which the particle's y-coordinate is increasing when y is equal to 0. So we're trying to find dy by dt. And we know that dx by dt is 3 centimeters per second. dx by dt is 3 centimeters per second. Okay, so dy by dt is equal to dy by dx times dx by dt. All right, that's what I know. And I know what dy by dx is. It's equal to 1 minus 2xy over x squared plus e to the y. And I know what dx by dt is. That's just 3. And if I have y is equal to 0, in the original curve, that means that x squared times 0 plus e to the 0 is equal to x, which means that 1 is equal to x, because e to the 0 is 1. So x equal to 1 and y is equal to 0. I can plug those in. I have 1 minus 2 times 1 times 0 is 0, divided by 1 plus, so 1 squared, plus, and then e to the 0 is 1, and that is times 3. So that all simplifies to 3 over 2 centimeters per second. Now, it's important that we learn how to apply the limit definition of the derivative in higher level, because there are some questions that might ask you to find the derivative of a simple function. So if, for example, I have f of x is equal to x squared, then I can use the limit definition of the derivative. I can say f of x plus h is x plus h squared, and I'm subtracting x squared and dividing by h. That simplifies to x squared plus 2xh plus h squared minus x squared, and the x squareds are going to cancel. So I get 2xh plus h squared. And now I can factor out the h, because the limit of h approaching 0 means h is not equal to 0. So I have limit of, as h approaches 0, of 2x plus h. That's equal to 2x. Now on the IB, the only examples that you will have of limit definition of the derivative are functions of the form, ax squared plus bx plus c. It'll only be done for quadratics. And the good news is that whatever answer you get, you can still check in your head whether you got the right thing according to the derivative rules. And you should always do that, because it's easy to make a mistake doing this. By the time that you're at the exam, it won't be so easy to make a mistake using the derivative of a polynomial. That's pretty easy. Yeah, this is a perfect example of what you might have to do. I'm going to give you I'm going to give you a minute to get ahead of me. 1 minute though, because we really have to race now. 20 minutes left. Okay, let's go over this. You guys can keep trying it while you're doing it, but I know that f prime of x is equal to the limit as h goes to 0 of f of x plus h. So in this case, I'm going to have 3x plus h squared plus 2x plus h, and then it's going to be minus f of x, so minus 3x squared minus 2x, and it's all being divided by h. Okay, that's the same as the limit as h goes to 0. I expand everything. I have 3x squared plus 6xh plus 3h squared, sorry. 3h squared plus 2x plus 2h. And then that is being multiplied by, I'm subtracting 3x squared minus 2x and dividing all of that by h. Okay, so that's all being divided by h. Let's cancel the terms that show up. So 3x squared with negative 3x squared, 2x with negative 2x, and I'm left with the limit as h approaches 0 of, and now I'm going to have just 6xh plus 2h plus 3h squared over h. You can cancel out the h now. Limit as h goes to 0 of 6x plus 2 plus 3h. Okay, and h is going to 0, so this just becomes 6x plus 2. Now I'm going to double check that works with what I have originally. If I take down the 2, that multiplies 3 gives me 6x, and 2x becomes 2. So this is correct, and I'm happy with my answer. Now, L'Hopital's rule. This is the last thing we're going to cover today. All right. And L'Hopital's rule gives us a more powerful way of evaluating limits when they are the form 0 over 0 or infinity over infinity. Okay. And the basic premise of L'Hopital's rule, the analogy I always give, is to imagine that you are driving to school, and your friend is also driving to school, but you live twice as far as they do. So this is, let's say, 2x, and this is x. Okay. And the question I want to ask is, at any given time as you guys drive towards school, you're driving at twice the speed. V is equal, so V, so this is, this is a velocity of V, and this is a velocity of 2V. At any given time, the ratio of your positions, the ratio of your distances are d1 over d2 is equal to 2. I mean, so it's like 2, it's going to be 2x over x at any point in time, which is always going to be 2, right? But I want you to imagine what happens in the instant, like as you're basically pulling up to school, you're arriving at school and you're about to park, and the distance from school is approaching 0. What is the ratio? Well, the ratio is going to continue to be 2, but where did that 2 come from? Why is it that one person is twice as far as the other? Well, because they're going twice as fast, right? And because they're going twice as fast, since they both have to arrive at the same time, and one is going twice as fast as the other, the one that's going twice as fast has to be 2 times as far as the other one at every point in time. And it seems obvious when I talk about cars moving at a certain speed, but now I'm going to talk about functions. I have 2 functions that are both approaching 0 or both approaching infinity, right? So they're both getting closer and closer to 0, and at 0 they're going to be undefined, so I can't actually plug in anything. What I can ask, though, is which one is going to 0 faster? If one of them is going to 0 faster, if it's going to 0 twice as fast, then it has to be twice as far away from 0, okay, than the other one. And that has to continue to be true. So what I can do, instead of looking at how far they are from 0, is just look at what happens in the limit to their speeds, the rates of change as we approach 0. Because the rate of change is the velocity or speed is inversely related to distance. So if a function is going twice as fast as another function, as x goes to 0, it must be twice as far away from 0 at every point, and therefore the limit would simplify to 2. And that means in general that if I have a limit f of x over g of x, where f of x and g of x are either both 0 or both infinity, I can find the limit, it's going to be equal to the limit of the derivatives of f prime of x over g prime of x. Now, it's not the derivative of the whole fraction. There's no quotient rule. It's the derivative of the numerator divided by the derivative of the denominator. It's exactly the same thing. Instead of looking at the values of the function or the distances, I'm going to look at the speeds and realize that the speeds have to tell me the correct values for the distances, okay? Now, this only works when I have 0 over 0, because if the 2 functions were not actually going to the same point, if they were not leading to some 0 over 0 or some infinity over infinity, then I would actually, this relationship I'm telling you about the distances doesn't work, because this only works when 2 things are going to the same place, okay? So here's an example. E to the power of 2x goes to infinity when x is very big. And so what happens to the limit of x minus 2e to the 2x divided by 3e to the 2x when x goes to infinity? Well, I can take the derivative of the numerator and the derivative of the denominator, and I get 1 minus 4e to the 2x in the numerator and 6e to the 2x in the denominator. And now I can tell that this 1 is going to be irrelevant. I can ignore the 1, because as x goes to infinity, it becomes inconsequential, and this becomes the limit as x goes to infinity of negative 4e to the 2x over 6e to the 2x, and that becomes negative 2 over 3. Now, I could kind of see that at the beginning by looking at the negative 2 over 3, but I didn't know what I could do with this x. And basically what this question is telling you, the reason that the x disappears is because x grows. If I were to graph x, it does something like this. Y is equal to x to something like that. And the exponent does something like that, which means as x goes to infinity, the exponent is actually going to be infinitely bigger than x. So the x is inconsequential next to e to the x. Another example when x goes to 0 is e to the x minus 1 over x squared. If I plug in 0, I have e to the 0 minus 1. That gives me 0. And 0 squared is also 0. So the limit is indeterminate. So I can use L'Hopital's rule. I take the derivative of the numerator. I get e to the x minus 1 divided by 2x. I'm going to have to do that now again, because if I do plug in 0, I get 1 minus 1 is 0 over 0. So I apply L'Hopital's rule a second time, and I get e to the x over 2. And that simplifies to e to the 0 over 2, which is just 1 over 2. Sometimes it's easier to factor out common terms rather than use L'Hopital's rule. Okay, if you have common factors, if you have 3x plus 1 and 3x plus 1, you can factor them out. It's going to be easier. I'm just saying that because sometimes you can do either like 5 steps of L'Hopital or 2 steps of L'Hopital and then cancel some common factors. So always be looking for common factors if you have them. I didn't understand the L'Hopital's rule. Can you please explain again? Yeah, so I'm going to, for those of you who did get it, you can try this question. I'm going to go back and try and explain it one more time. Okay, so I want you to imagine two functions that are both going to 0. Okay, so this is the coordinate axes, and two functions are both going to 0. Okay, but they're going to 0 in different ways. All right, and I'm just gonna make it a simple example and say this is f of x and this is 2f of x. Okay, make it a simple example just for the sake of understanding. And so I know that if I actually took the limit of as x goes to 0 of 2f of x over f of x, that's just going to be 2 because there's a 2. But let's say I was just looking at the graphs and I didn't really know that. And I zoomed in on the graphs and I would see something like this. So I would see, like that and like that. Okay, and they're both converging at 0. Now, what L'Hopital's rule is saying is that if this curve, I want you to imagine I'm going to draw an arrow in pink that goes forward like this. Okay, so it's going from here to 0. Okay, it's going like that. And this arrow in the same place is less steep. It's going like this. Okay, and the arrows both still meet. They're going to intersect if they kind of kept going in the direction that they're going. But one of them is going faster than the other. It just has a greater slope. In this case, a more negative slope, but it doesn't really matter. It has a more negative slope, and that matters because if I know that the two functions have to meet at 0, and one of them is going faster than the other, I mean, literally imagine that you have two people on a track, and they're both going to arrive at the finish line at the same time. But one of them is going twice as fast as the other, right? You have one person going twice the speed of the other, but they're going to meet at the same place. It means that the person who's going faster is twice as far from the finish line because he's going twice as fast, and yet he's going to get there at the same time as a person who's half the distance away. And so just because of that relationship, which I think we understand in the physical world, we can apply the same thing to functions and say that I have a function that's moving towards the destination twice as fast as the other one. Therefore, at any given point in time, it has to be twice as far away from the destination. Otherwise, the distances wouldn't line up because I know the functions go to the same place. Okay, so that's what L'Hopital's rule is saying. All right, last question of the day, a L'Hopital's rule example. I'm going to give you 2 minutes to start. So if I plug in 0 into this function, I get e to the 0 is 1 minus arctan of 0, that's 0 as well, minus 1. So I get 1 minus 1 is 0 divided by 0. So I have a limit 0 over 0. So I use L'Hopital's rule. And I say that the limit as x goes to 0, it's going to be equal to, now I take the derivative of the numerator and denominator. Derivative of e to the 3x. I'm going to actually, I need a good bit of room. So I'm going to say this like that. 3 e to the 3x for e to the x. And then for arctan of 3x, well, arctan of x has a derivative of 1 over 1 plus x squared. That's not equal, I should say, has a derivative. So that means that arctan of 3x has a derivative of 3 from the derivative of 3x divided by 1 plus, and now 3x squared is 9x squared. So this is plus 3 over 1 plus 9x squared, and the minus 1 goes to 0, so it just disappears. And now in the denominator, sorry, I have x squared, which becomes 2x. Let's check what happens. If I plug in x is equal to 0, I have 3 e to the 0 is 3 times 1 is 3, and then I have 3 over 1 plus 9 times 0 is 3. So I'm going to get, and sorry, this is supposed to be a minus because there's a minus arctan of x. That gives me 3 minus 3 is 0 in the numerator and 0 in the denominator. So still have 0 over 0. So I need to use L'Hopital's rule again. Let's do it again. The derivative of 3e to the 3x is now 9e to the 3x. So I have 9 e to the 3x. And I can write this little piece here, or actually I'll write it here. It's going to be clearer as 3 times 1 plus 9x squared to the minus 1. Okay, which means that now I'm going to have minus, and minus times minus 1 for the power, times 3 times 1 plus 9x squared to the minus 2, then times the derivative of the inside, which is 18x. Okay, and that is going to be divided by, it's going to be divided by 2x. And now I'm letting x be equal to 0. Oh, sorry, divided by just 2. That's going to go away. It's going to go away. And now, if I plug in x is equal to 0, I would get 9 minus 0 over 2, which is just 9 over 2, and that is my answer. Okay, so it's very important that you know when to stop using L'Hopital's rule and not just keep going. So after every step, you have to check if you are done. And in that case, I was done after 2 steps. Usually on the IB, it will take 2 to 3 steps. It usually won't be 1 because that would be too easy. And anything more than 3 is just, it's getting very tedious. And there are better ways to do it using Maclaurin series. Okay, so that is everything for today. Thank you everyone for sticking with me. Other than that, that's everything I had. Well done for sticking through to the end. It was hard work today. I'm also going to stop the recording, so anyone watching the recording, bye-bye.